For this, we need to write the set of kinematical equations. For this purpose, we need to draw the rod and mention the accelerations of the center of mass along x-axis and y-axis, as we mentioned in the free body diagram. And this point is P. And we have to mention the angular acceleration of the rod. This diagram is not free body diagram, this is kinematical diagram. And the free body diagram, what we have mentioned earlier, can be called kinetics diagram. Kinetics. And this diagram is kinematical diagram. That is the diagram of kinetics or dynamics diagram. Using the kinematics of motion of the rigid body, there are two types of motion called translation and a rotation. Since the point P as 5 hertz is fixed or stationary as per the given physical condition, acceleration of the point P or velocity of this point P is 0. But acceleration of this point P is not equal to 0. That's interesting. Since this point P is not moving because it is pivoted, its velocity is 0. And velocity of this point P is equal to velocity of this point P with respect to C plus velocity of C according to Galilean transformation of velocity. In this diagram, we can show that with respect to center of mass, the point P moves in this direction, that is VPC. That's equal to L by 2 into omega, as you discussed in kinematics of rigid body. And if we assume that center of mass moves down, BC is down, bring the velocity of center of mass to this point. So when you bring the tails of these two vectors to a point, VPC and VC are oppositely directed. Therefore, we can write this as minus L by 2 into omega, that's plus L by 2 into omega, Jkf, plus Vc is minus V Jkf. we are getting Vp. Since Vp is equal to 0, we can write V is equal to L by 2 into omega. Differentiating both sides, dV by dt is equal to L by 2 d omega by dt. And dV by dt is the rate of change of speed of the center of mass, that is equal to the acceleration of the center of mass in which direction? In y direction. Is equal to L by 2 into d omega by dt, that is alpha. This is one equation we are getting, and name it the fourth equation. Now let us try to build the fifth equation. So you can document this equation as fourth equation. We need how many equations? Two equations more. One equation already we have got. We need one equation only, and that is possible only when we consider the motion or the kinematics along x direction. The acceleration of C along x axis. Here the rod is moving. Let us assume that the center of mass of the rod moves with the velocity v down, and the angular velocity of the rod, let be omega. So this point velocity with respect to the center of mass, that is Vpc, will be equal to L omega in this direction, and the center of mass of the rod will move down, that is Vc is down. You bring Vc to this point, Vc is down, Vpc is up. At the velocity of this point is equal to L by 2 omega up, and Vc, that is equal to V down. But this is 0 because this is stationary. When this is not moving, V will be equal to L by 2 into omega. Taking the derivative of both sides, we are getting dV by dt is equal to L by 2 d omega by dt. Rate of change of speed of the center of mass is equal to the acceleration of the center of mass along tangential direction. Here one interesting thing you have to note. This is the pivot. This is the center of mass. The center of mass is rotating in a circular path. For this case, the center of mass has two accelerations. If the angular velocity of the rod is omega, this point say moves in a circular path with respect to this pivot P. Therefore, it has one acceleration towards the center of the circular path, another acceleration is directed along the tangent. this acceleration is called tangential acceleration. In this case, we can call it AY because it is directed along y axis, and the acceleration of the center of mass or midpoint of the rod is directed towards the center of the circular path, that is the pivot. This is called radial acceleration, or we can call it acceleration of the center of mass along x direction, and this is pointing along negative x direction. So, better to write in this way: A tangential, that is equal to AY, is equal to L by 2 into alpha, following the kinematics of circular motion, and radial acceleration can be written as r omega square. R is equal to L by 2 into omega square. So, using the simple concept of circular motion of this point, we can write x is equal to minus L by 2 omega square, because I have taken this direction as positive x direction, but it is accelerating along negative x direction. Therefore, x is equal to minus L by 2 omega square, that is none other than the radial or centripetal acceleration. Another acceleration, that is the tangential acceleration, or in this case that is acceleration along y direction, that is L by 2 into alpha, because alpha of the rod I have assumed in this direction. Alpha about this point is equal to alpha about this point. Omega about this point is equal to omega about this point. Alpha and omega, they do not depend upon the point of reference. But in this case, this point moves in a circular path. Therefore, we have got another two equations by using the kinematics of circular motion. We can call it equation 4 as we have mentioned. This is another way of writing the same equation, and this is the last equation, equation 5. In this way, we have now 5 equations and we have 5 unknown quantities. Now, the final step is to solve for the unknown quantities. Let us document all this. The 3 equations. Here we have 2 equations. Ay is equal to L by 2 into alpha, equation number 4, and x is equal to minus L by 2 into omega square, equation number 5. In the final step, number 3, solution of the equations. Generally, we can use the kinematical equations. X is equal to minus L by 2 into omega square. In this dynamical equation, Rx is equal to m into x. So, using equations 1 and 5, we have Rx is equal to m into minus L by 2 omega square. Rx is equal to minus m L by 2 into omega square. Answer. Next, we are using the fourth equation to get alpha. We substitute Ay is equal to L by 2 into alpha. From equation number 4 in equation number 2. Using equation number 2 and 4, we have Ry is equal to m L by 2 into alpha plus g. Then we can substitute alpha to get Ry, or you can substitute Ry to get alpha. So these two equations, if you solve, we can get Ry and alpha. Let us write alpha is equal to six Ry by ml plus g. So we are getting ml by 2 into 6 Ry by ml plus mg. ml will be getting cancelled, 2 and 6. So if you cancel, we are getting 3 in the numerator, that is 3 Ry plus mg is equal to Ry. Here we have all 5 equations. This is absolutely correct. If you redraw the FBD, this is Ry, this is Rx, this is mj, this is x, this is ay, and this is alpha. Rx is equal to m into x, same direction, absolutely correct. Ry is up, net force along y direction, Ry. Mg is down, minus mg. Or you can just write net force along y direction is equal to mass times acceleration along y direction. Here there is a problem. When you are considering the net force, when you consider the net force acting on the body along y direction, we have Ry in upward direction plus j cap, and gravity in downward direction minus j cap. That is equal to m. Acceleration of the center of mass along y direction I have assumed down. Therefore, it will be minus ay j cap. If you simplify it, you will get Ry is equal to m g minus ay. There is a problem here. Therefore, we have to rectify it. Sometimes we get wrong equation. So, before you solve the equations, better to check the equations again. So, we have Ry is equal to ay minus g, and other equations are absolutely correct. Now, instead of plus, if you write minus, so it will be minus, it will be minus, it will be minus. Then we are writing Ry is equal to mj by 2. That is the reaction force along y direction. Along x direction, the reaction force is negative. This means that the pivot will pull the end of the rod or pull the rod in this direction. We have assumed the positive direction, but we got negative result. It physically signifies that the direction of the reaction force on the rod along x direction will be directed towards left. So, the real diagram, the Rx will be pointing towards left, and Ry we got positive answer, and we have assumed that Ry is vertically upward, and we got positive answer. So, our assumption is correct. This is the real diagram, real or physical. This is assumed. Next, the net reaction force is R is equal to Rx I cap plus Ry j cap. So, its value magnitude is equal to Rx square plus Ry whole square. What is Rx? That is ml omega square by 2 square of this. What is Ry? That is mg by 2 square of this. Sum them up and you have to take the square root. This is the magnitude of the reaction force. If the initial angular velocity of the rod is 0, if the initial angular velocity of the rod given at the given position or given instant is 0, then this factor will vanish. The reaction force is totally vertically upward, and that is equal to mg by 2 under this condition. If the rod is released from rest, then omega is 0 at the given position. If the omega or the angular velocity of the rod is non-zero, then we must have the horizontal component of the reaction force, or the reaction force acting along the rod in negative x direction, a pulling force. The pivot will pull the rod in this direction. However, the pivot will push the rod up. When you take omega is 0, this force is non-zero. Always the pivot is pushing the rod up. So omega is non-zero, we can get non-zero reaction force Rx. So the net reaction force is equal to sum of these two reaction forces. This will be directed in this direction. This will be the components. This is the net reaction force. And of course, you can calculate this angle also. The angle you can calculate. The angle can be calculated by taking the tan inverse Ry upon Rx. And here, if omega is non-zero, then you have to write Ry our as usual result, that is mg by 2, and for non-zero omega, Rx will be equal to L by 2 omega square. So 2 will be getting cancelled. Here Rx will be equal to m into L omega square upon 2. Will be getting cancelled. In this way, we are getting phi is equal to tan inverse J by L omega square. Answer. So this is a complete analysis of the reaction forces, the accelerations, angular acceleration, the linear accelerations of the center of mass at the given position or given instant. Next we can calculate the value of alpha. When we have, next we can calculate the value of alpha. We have got Ry is equal to mg by 2. Just to substitute Ry in the equation number 3. Ry is equal to ml by 6 into alpha. At Ry we have got mg by 2, that is equal to ml by 6 into alpha. M will be getting cancelled. So alpha will be equal to 3g by L. So let us tabulate all these equations we have obtained. Before solving these equations, we need to check each and every equations. How many equations we have got? 5 equations. What are these equations? Dynamical equations and kinematical equations. How many dynamical equations you are getting? 3 dynamical equations. 1 torque equation and 2 force equation. There are 3 dynamical equations you are getting. How many kinematical equations you are getting? 2 kinematical equations you are getting along x direction, along y direction, or along the rod or normal to the rod, or along the tangent, along the radius. Let me redraw the diagrams, the kinetics diagram or dynamical diagram or free body diagram and the kinematical diagram. Here is the pivot P. Here is the center of mass. See, this is the kinematical diagram. In kinematical diagram, you should not write the forces and torques. You should only mention the velocities and accelerations. Here omega is given. Initially, let us assume that there is a non-zero angular velocity. Therefore, velocity of the center of mass is equal to r into omega, because the center of mass is moving in a circular path whose center is the point P, the pivot. While it moves in a circular path, the center of mass will have two accelerations, one radial, one tangential. Since angular acceleration of the rod is alpha, the acceleration of the center of mass with respect to the pivot will be radial acceleration, that is r omega square, and tangential acceleration, that is L by 2 into alpha, or you can say r into alpha, where r is equal to L by 2. So, you just write AR is equal to r omega square, r is equal to L by 2 into omega square. AR is equal to L by 2 into omega square. And that is pointing along negative x direction. So, AR is equal to, or you can just write x is equal to minus L by 2 omega square, because we have assumed the acceleration of this point along positive x direction, but actually this is accelerating along negative x direction. Therefore, it is minus L by 2 into omega square is equal to x. And AT is equal to r into alpha, and r is equal to L by 2. Therefore, AT is equal to L by 2 into alpha. That is another equation. And we have taken downward as positive y direction. So, we can just write AT is equal to AY. So, x is equal to minus L by 2 omega square, and AY is equal to L by 2 into alpha. We have got three dynamical equations, and these two kinematical equations we have to use. So, this equation number 4, equation number 5. So, this is the subject matter of the kinematical diagram, the output of the kinematical diagram. Here we have not shown any forces or the torques. We have shown the velocities and acceleration x and ay. We have assumed, but actually x is negative because this point C is accelerating towards the center of the circular path in negative x direction at this instant. This is called free body diagram, or this is called kinetics diagram. In this diagram, we can show the forces Ry, Rx and mg along with the accelerations ay, x and alpha. Linear accelerations of the center of mass and angular acceleration of the rod. Either you can write alpha in this way or in this way or in this way, your wish. The equations along the x direction, net force is plus Rx is equal to mass times the acceleration along the x direction is plus x. Equation number 1. Along y direction, Ry is up, that is positive, and mg is down, that is negative, is equal to acceleration we have taken down. If up is positive, down is negative. Or if you do not like this concept, you just follow vectorially. Ry vector plus mg vector, this is the net force in vertical direction, and that is equal to mass times acceleration of the center of mass, that is C. Jkf mg is minus mg Jkf is equal to m into ay is minus ay Jkf. Then you are getting the correct equation. R minus mg is equal to minus may. Therefore, R along y direction, Ry is equal to mg minus ay. Probably you have got wrong equation because of the silly mistake. Therefore, you should strictly follow the vector equation. Fi vector is equal to Ry vector plus mg vector is equal to mass times the acceleration of the center of mass along y direction, that vector. If you don't follow it, sometimes you can write m into ay minus g as you have done, and you got wrong result. Therefore, always follow the concepts of vector. This is equation number 2. This is force equations. Next, the torque equation about the center of mass. Tau c vector is equal to IC into alpha vector. As I told, these two forces pass through the center of mass, they cannot produce a torque about the center of mass axis or z axis. So, the torque is produced by this force, that is equal to Ry into L by 2 in which direction? In negative z direction or clockwise direction, into minus k cap is equal to IC is the center of mass axis, the moment of inertia about the centroidal axis along z direction, that is ml square by 12 into alpha. Alpha we have assumed in clockwise manner is minus alpha k cap. This gives us Ry is equal to m L by 6 alpha. This is equation number 3. So, torque equation and force equation. Two force equations, one torque equation, 3 dynamical equations, and 2 kinematical equations along x direction, y direction, or radial direction and tangential direction. 2 kinematical equations. So as a whole, as a total, we are having 5 equations and 5 unknown quantities. The unknown quantities are x, ay, rx, ry, and alpha. 5 unknown quantities, 5 equations. Very nicely you can solve in the third step. Let us tabulate all these equations. Equation number 1, Rx is equal to m into x. Equation number 2, Ry is equal to m g minus ay. Equation number 3, Ry is equal to ml by 6 into alpha. Equation number 4, x is equal to minus L by 2 into omega square. Equation number 5, ay is equal to L by 2 into alpha. Let us solve all these equations. Step 3, we need to solve all these equations. So our physics is over, just we have to apply our mathematical brain to solve all these equations. You can use equation number 4 and equation 1. Substitute the value of x from equation 4 in equation 1. Equation 1 and 4 give us Rx is equal to minus m, x is equal to minus L by 2 omega square. So you are getting Rx is equal to minus m L by 2 omega square. So negative sign physically signifies that we have taken Rx in this direction, we are getting negative result. Therefore, this assumed diagram and this is the actual diagram. This is assume this is actual. Actually, the direction of Rx is towards negative x direction. We have assumed in this direction and we got negative answer. Therefore, we have to alter the direction of Rx as you have assumed. By altering the assumed direction, we are getting the direction in leftward direction. Next, from equation 5, you use ay and substitute this ay in equation number 2. Equation 2 and 5 give us Ry is equal to m a minus ay. What is ay? L by 2 into alpha. And we have not used this equation number 3. You can Put the value of alpha from equation 3 in this new equation to get m a minus L by 2. What is alpha? 6 Ry by ml. 6 Ry by ml. This is equal to Ry. This gives us, this is not A, this is G, mg minus 3 Ry. This is equal to Ry. And Ry is equal to mg by 4. This is the correct answer. We got wrong answer because instead of writing this equation Ry is equal to m into Ay minus L by 2 alpha, we wrote m L by 2 alpha minus Ay. That's equal to Ry. This is a wrong equation. This is a correct equation. We committed the mistake due to the incorrect direction of the forces and assumed direction of acceleration of the center of mass. Well, when you substitute the value of Ry in this equation number 3, Ry is equal to ml by 6 into alpha. We substitute the value of Ry here, that is mg by 4 is equal to ml by 6 into alpha, and here we are getting alpha is equal to 3 by 2 g upon L, answer. And Rx already we have got, Ry we got, and Ry is equal to mg by 4. Rx is equal to minus ml by 2 into omega square. Alpha we got. Now the accelerations of the center of mass. X is equal to minus L by 2 into omega square, answer. Ay is equal to L by 2 into alpha. What is alpha? 3g by 2L. Therefore, Ay is equal to 3g by 4, answer. We got Ay, we got Ax, we got Ry, we got Rx. They may ask you to calculate the total acceleration and total reaction force. The net acceleration is equal to Ax vector plus Ay vector. Its magnitude you can calculate. That is equal to L by 2 into omega square, square of this plus 3g by 4, square of this, and take the square root. If initially it is given that the rod is released from rest, then you can substitute omega is 0 and you are getting 3g by 4 as the total acceleration that is vertically downward. But this is a more general solution, answer. And angle, as I told, you can calculate the angle. Here we have the acceleration Ay and this is x. The net acceleration of the center of mass C is A. A is equal to L by 2 omega square of this plus, that's omega square, plus 3g by 4 square of this, square root. This is equal to L square omega 4 by 4 plus 9j square by 4. And we can get L square omega 4 plus 9 j square square root by 2. And direction, you can get, this is suppose phi. Phi is equal to tan inverse x by, this is x, this is ay, x by ay. So tan inverse, what is x? L omega square by 2. What is ay? 3g by 4. So is equal to tan inverse L omega square by 2 into 4 by 3g. So at last we are getting tan inverse L omega square by 2L omega square by 3g. Answer. Next they may ask you to calculate the total reaction force, magnitude and direction.